Now that you know about what the difference is between a vector and a scalar, let's take a look at what we're actually going to use vectors for in this class. When we drew our maps of, or when we worked with the maps of the schools, the school where we took a look at your displacement versus your distance, we used the hallways as our pathways, but then for displacement we said that we didn't care about whether you could actually travel that direction. If we were to imagine a similar situation where we had a series of grids, or a grid pattern with a series of roads, say this is, I don't know, New York City or something like that, and let's imagine that I drew these correctly and they're all equally spaced. When you go through, we can figure out a pathway to go from 2 points. So say we wanted to go from this blue point A here to this blue point B up here. So the blue pathway means that you could go any number of ways. You could go down this way and then up this way. You could go up first and then go over second. We'll put arrows here so we know what direction we're headed. You could go in a zigzag pattern, go up, then over, then up, then over, then up, then over. You could go in any number of different ways to get from A to B. But you could also go, if you were a bird or if you could float through walls, you could go from here to here. And so this red vector here, this is called our displacement vector. Right? And we saw that when we took a look at the school. That was the direction of our displacement and the length of our displacement from location A to location B. Now, when we talk about vectors and vector displacement, what we want to do is we want to talk about resolving the vector. Resolving the vector. And resolving the vector here literally means breaking it into components. So we are literally breaking these vectors into components. Now, if we were to say that each of these was a size of 1, and each of these was a size of 1, then our resultant displacement vector here has the following components. Saying that north is up, that means that we're going over 3 to the right, or to the east, and then we're going up 3 to the north. So if I were to break this red vector into components, I would say that my red displacement is given as 3 units to the east, and then 3 units north. So this vector is given by these two vectors, which means that if I were to go 3 units to the east and 3 units north, I could get exactly to where I needed to, vector location B. Now, that means that we're forming a triangle here, where our bottom component of the triangle has a length of 3, and our side component of the triangle has a length of 3, and in the end, then we are connecting those with our red displacement vector. And so this is where the trig that you worked with came in yesterday, because if this side is 3 and this side is 3, we can figure out what this side is here. Because east and north are perpendicular to each other, and so we form a right triangle, and with a right triangle we can say that this third side length here, which we will call r, r squared is equal to both of the sides squared and summed. So this is 3 squared plus 3 squared, which is 9 plus 9. So r squared is equal to 18. So that means that r is equal to 3 times the square root of 2. And our unit for this one is blocks. 3 times the square root of 2 blocks. We can also then figure out what this angle is here, angle theta, by understanding that if this is 3 root 2 here, we can use tangent, cosine, or sine to figure out what this angle is. Because we were given these sides as our initial side lengths, I would recommend using tangent, and we'd say that the tangent of angle theta is equal to, remember, SOHCAHTOA. The tangent of angle theta is equal to the opposite side over the adjacent side, or 3 over 3. When you type that into your calculator, 3 over 3 is 1, so we're saying that the tangent of this angle is equal to 1. Now, you may recognize that whenever the tangent is equal to 1, that means that our x and y components are the same. But if not, it's not always going to happen. So we might as well just take the tangent inverse of both sides, or the arctan. So if we take the arctan of both sides, we end up with theta equals arctan of 1, which is going to give us a theta value equal to 45 degrees. So we've got this theta value of 45 degrees, we've got this r value of 3 times the square root of 2, and that's a way to describe our vector. What this means is that we've got 2 ways that we can describe our vector. We've got way 1, which is the direction plus the magnitude of the vector. And we've got way 2, which is the components of the vector. Now, way 1, we're going to list our magnitude first. So our magnitude is 3 times the square root of 2. Our unit is blocks. And this is going to be at an angle of 45 degrees. The second way that we can describe our object is with components, and so our components were how far east and then how far north we went, so it's east/west and then north/south. So in that case we went 3 blocks east, and we also went 3 blocks north. So those are our 2 components of this vector. So we have 2 different ways that we can describe it. So what that means is that we have 2 different vectors that are both describing the same motion. So if I started at point A and I went up at an angle of 45 degrees and I went the equivalent distance of 3 root 2 blocks, 3 times the square root of 2 blocks, then I would end up at point B. Alternately, I could go 1, 2, 3 blocks to the east and 1, 2, 3 blocks north, and I would also end at the same location. So we can use vectors for displacement. We can also use vectors for velocity, and velocity is where we're going to be using it mostly during the second quarter, is looking at the velocity of an object undergoing what's called projectile motion, or we can also use it for forces, but we'll start with velocity for projectile motion. So imagine, if you would, a grid again, and we've got a north going this way, and I have an object that is traveling up at a speed of 40 meters per second, and it's going at an angle that is north of east, that's this angle right here, of 30 degrees. And I want to know, this object is traveling at 40 meters per second, so what are the equivalent eastward and northward velocities for an object going 40 meters per second? Because you can imagine, if we went east and then north for the same amount of time that we went this way, we could figure out a velocity in each of these directions that would be equivalent to this velocity here. So to do that again, we resolve our vector into components. We've got a hypotenuse of 40, and we're looking for this side here, which I will call V east, and this side here, which I will call V north. Now, if this angle in the middle here is 30 degrees, then we can say that the sine of 30 degrees is equal to SOHCAHTOA, the opposite side, Vn, divided by 40, and similarly that the cosine of 30 degrees is equal to Ve over 40. So now we solve this, we bring the 40 in each of them over to this side, and we're left with this, that the northward velocity is equal to Vn times the sine of 30, and the eastward velocity, nope, sorry, just kidding, Vn is equal to 40 times the sine of 30. And bringing this over here, we end up with V east is equal to 40 times the cosine of 30. Now, sine of 30 is 1/2, so our velocity in the northward direction is 20 meters per second. And this over here is 3 root 2, so this is 20, cosine 30 is 3 root 2, so this is 20 root 3 meters per second. So that means that if we had an object that was simultaneously going 20 times the square root of 3 meters per second in the northward direction, eastward direction, and 20 meters per second in the northward direction, it would in essence be traveling 40 meters per second at the angle of 30 degrees north of east. Now, a couple of things to notice. Take a look. The units here for our hypotenuse are the same as the units that we have for the resolved components. That's a really important part. We can also use velocity vectors when we're talking about an object that is kicked from the ground. So let's imagine, if you would, a ball that is kicked off of the ground. Here's my ground. So we have a ball that's kicked off the ground, and when it's kicked off the ground, it undergoes a parabolic path, something like that. And I want to know, because remember, we've been dealing in one dimension so far, so now we're encouraging ourselves to look at 2 dimensions. I want to know 2 things. I want to know how it moves in this direction, the x direction, and I also want to know how it moves in this direction, the y direction, because my velocity in the x direction is going to give me information on how far it goes, right? This is my x component of our displacement, right? X displacement, and my velocity in the y direction is going to give me information about how high it goes, how long it's in the air, and what its velocity is at the ground. And so we think about it the same way. If this is 20 meters per second, which is pretty fast for a ball being kicked, but that's all right. We'll assume that I can kick very strongly. And we have an angle of 60 degrees here. That means that we again have a nice right triangle where we have a hypotenuse of 20 meters per second, and we are looking to resolve our x components and our y components. So Vx here and Vy here, right? So we would say that if this is angle 60 degrees here, that Vx divided by 20, that's equal to the cosine of 60 degrees, and the sine of 60 degrees is equal to Vy over 20. And so again, we'd have a similar situation. Rearranging that equation, Vx equals 20 times the cosine of 60, and Vy equals 20 times the sine of 60. And these are both in units of meters per second. So this one ends up being 10 meters per second here, and this one ends up being 10 times root 3 meters per second here. What that means is that an object that is kicked at an angle of 60 degrees off the ground at its initial speed of 20 meters per second allows us to think about the vertical direction as an object that is traveling at 10 times the square root of 3 meters per second upward initially. So this is like I throw something upward in the air at that speed. And also think about an object that is moving at 10 meters per second in the x direction. So now I can figure out if it stays in the air for 15 seconds, how far does it go, how high does it go, all of those types of things. So then next time we're going to be talking about vector addition. And this is looking at the ideas of if I have a vector that goes in this direction, and then I want to add to it a vector that goes in this direction, how do I do that? And the hint that I will give you, the kind of preview hint that I will give you, is think about Google Directions. Google Directions. Think about when you get directions from Google, how do you string those together? Because that's really what this is. This is a displacement. Think about this as a displacement vector. I'm going from here to here, and then I go from here down a little bit, you can kind of visualize what's going on. That's all for today.